Okay, so we're into lesson 5, talking about wave interference, Young Double Slit experiment. So you were asked in lesson 4 to prove if light is a particle or is a wave. So for the longest time, scientists have been having a hard time saying that light is a wave. Okay, so you would have doing some reading already, because one of the biggest thing is the interference of light, of wave. Okay, so in lesson 3, we already talked about the 2-point source interference, which is this picture right here. And we know that if I have two water waves and when they interfere with each other, I should have like supercrest, supertroph, and some nodal line, and I can study the interference. And so that was the biggest challenge in the science society. They're like, well, if you say light is a wave, how come when I put two candles together, and when the light wave interference, I actually don't see constructive and destructive interference that are happening from the candle? And the reason now we know it's because the light waves is very, very small. So wavelength of light is really, really small. So we're talking about like 750 times 10 to the negative 9 meters, like into a nanometer thing. But then with the candle being so big, it is not going to show the interference. So Young was actually so smart that he's like, well, wait a minute. Instead of having two sources of light and trying to see the interference pattern, what he did is he had a thin sheet of thing, and then he actually punctured two holes in it. I'm making this really, really, really big. He actually punctured two holes, and he called it the Young Double Slit experiment. If you actually take a look at a real life what a double slit is, you're talking about like the distance between here, like you probably barely can see. We're talking about times 10 to the negative 6 meters. That's like the distance of the width that we're talking about. Remember how we used the D, distance between the two sources? We're talking about really, really small distances, right? But because he did that, he now is able to see it. So what I wanted you to do is make sure that you would watch this video. I posted in the classroom just to see. This guy, he actually carried around this box, and he actually did the Young Double Slit experiment and walked around and explained it. Okay, so let's read through this. So Thomas Young, he conducted an experiment, and he's using one incandescent light source, and he shines it through two pinholes. And each of the pinholes were acting as a point source of light. And since a single source is used, the benefits of it is that the number one thing that you need to understand is, number one, is that all the waves are in phases. Okay? And the interference pattern was observed on a screen to produce a bright and dark bands. These are called the interference fringes. And you would see light that are bright, we call it the maxima, and and then some dark lines, we call it the minima, that is produced by the interference of light. If you were in the classroom, and if I actually see you, this is what we would do. We would actually take a laser pointer, and we would have a piece of glass that have these double slit in there, and we shine it through, like bad drawing of the glass. But if I were to draw the glass, like you would have a thin glass with like very small interference pattern, and we would tape a sheet of paper on the wall, and you would actually be able to see bright light, dark light, bright light, dark light all the way through. And the reason why that you would see them is if we go back to this picture right here, if I make a copy of it and make it bigger, and I'm going to add a page. If I'm able to make this bigger. Okay, so remember how we talk about there is the constructive and destructive interference, right? Let's make a pink dot to be a constructive interference. Say, for example, when they are the same line, like if they're crest with the crest, it would be a bright line. So this is my bright line. Okay, nodal line happens with, let's make it little blue, is with the crest and the trough. So these are the nodal line. Right? And then like say in the middle, we got the bright line in the middle. So that those are the pink. So like these are the bright line. And then there are the nodal line, which is like right beside it. These are the nodal line. This is when the crest and the trough, they cancel each other. So imagine this. If I put a piece of paper and I put it across here, anywhere that crosses the bright line, I would see the bright. So in here, on the piece of paper, I would actually see the bright line here, the bright line here, like all those stuff. Light. Bright is purple. Like, so anywhere on this sheet that actually lines on the crest and the crest, those are the bright line that's going to show up. Okay, but at the same time, anywhere that is the places where it's a cancellation, I would have dark line. All right, so you would actually be able to see patterns that are showing up on your wall with the bright and the dark line. Okay, so and then now because we understand the interference pattern, they're now studying it the same way that we did as a 2-point source interference. So right in the middle, you would always have bright lines. So just like the picture I was showing you just now, right in the middle, which is right here, this is the middle, there's always the bright. Okay, and then you would see that this is your nodal line. This line is the nodal line. And this line is the nodal line. Okay, and then let's see what happened with that. So if they shift the path difference by half a wavelength, you would notice that you would have a dark line in here. So this is now your dark line. And if you shift it over by 1 wavelength, you now have another bright. So this is a bright, this is a bright, and this is a dark. Okay, so it all depends. The path, though, I don't know if you remember path difference. If I shift it, it would be a destructive interference and then a constructive interference depending on how much you shift it. Okay, so if you want to read into details, you're allowed to. So I don't know why my equation is not showing up in here, so I just hand wrote it. Okay, so I think in your note it should show up. So basically, it's very similar to what we have done in lesson 3 when we talk about the interference of 2-point source. What they notice is that every time when it's a destructive interference, they found this relationship. Sine of theta n is equals to n minus half lambda over d, with n being the node, like which number of nodal line, lambda being the wavelength, and d means the distance between the slit. They found that the sine theta equals to that. And so this equation is probably the only equation you would be using. Okay, basically, whenever we study these Young Double Slit, we would only be talking about the minima, okay? The dark. We always just talk about the dark fringe, okay? Even though they gave you the equation for the maxima. This is the constructive interference. But all measurements that we would be doing are always measured in between the dark line, because the nodal line is the line that will be easier for you to tell the exact 0 point between the bright spot. Okay, so we probably very unlikely would use this. Okay, and the biggest thing with these types of questions is you need to know the wording for it. So make sure you go back to, you know how like for the last lesson, we kind of review some of the key words. Just know what your lambda is, what your D is, and what they stand for. Okay? All right, and then realistically speaking, you will not be able to do the measurement for the wavelength of light. Like there's no way you can measure that. It's going to be an indirectly thing. So what they have also found is they can actually measure the X, okay? We call it the XN. So basically the distance from the nodal line. So here it is. So they have been using the ratio for X over L. And X is the distance of the nodal line from the center line on the screen. So if you see, this is your X. So imagine if you are standing here, this is you're standing here. Okay, you have a sheet of paper of where the screen is. Okay, you can easily measure L by measuring how far you are from the screen. Okay, and then remember how we said you can actually see the bright and dark on the wall, and that's how you measure the XN, because the XN is from a dark line to the center line. Okay, and with that, they found that the relationship with that, it's easier to measure if I have the xn, basically between the dark line and the dark line. So this is the dark line, okay? This is dark. And then on the other side, there's also the dark, okay? And in between that, you can then measure what is the x1. This is x1, xn, okay? And then so on and so forth. So even sine theta would be hard to measure because that's angle theta. So it depends on what they give you in the question, okay? And then they found that the relationship is half a wavelength divided by the distance between the slit, okay? Which is this distance right here, okay? All right, so then they found the general equation. The only thing that you need to watch out for is the L is here for the double slit, okay? And remember from the 2-point sources, the L was here, okay? So this is with the double slit, your L, it's actually, just because in terms of the angle, it's so small. Angle theta is so small that they're just making an approximation. All I'm doing is measure from wherever the double slit is to the screen, and then we're just going to call that distance L. And this is another relationship that they found. Okay, delta X over L is equals to lambda over D. So L is still the distance from here to here. So if I measure the distance, this is L. They found that between dark space, and so I need you to know what delta X is. Delta X is between any two nodal line. Okay, delta X is distance between adjacent nodal line. Okay, and notice that your X1, this is something else that I need you to pay attention to. Your X1 is from the center to the first nodal line. Your X2 is from the center to the nodal line, and the X3 is so on and so forth. But what is delta X? Okay, delta X, I'm going to change color. If you take a look at what delta X is, delta X is between each nodal line. The only thing I want you to pay attention to, what is the delta X in the middle? Okay, so just be careful. I'm just going to magnify this. Okay, for a young double slit, your delta X is actually equals to 2 times X1. Okay, do you see X1 what it is? And do you see how delta X goes in right here? Okay, yours, hopefully your picture is better. Okay, this is delta X, is 2 times the X1. Okay, so just be careful with that. But normally they would just tell you, oh, the distance between 5 nodal line. And let's talk about that too. Okay, if we said delta X is the distance between adjacent nodal line, and they tell you that you have 6 nodal line in total, is say 5 centimeters. Okay, I'm just making this up. So if I start drawing nodal line 1, 2, 3, 4, 5, 6. Question for you is, how many delta X is there between 6 nodal line? Delta X is distance between adjacent nodal line. So this is 1 delta X. Here is another one. 3, 4, 5. Between 6 nodal line, they're actually 5 delta X. And they're telling you that the distance between 6 nodal line is 5 centimeters. So it's not 6 delta X equals to 5. It's actually 5 delta X equals to 5. So make sure you draw the picture. Every time when they say distance between nodal line, draw the picture and figure out how many delta X there are. Okay, so let's see what they give you. You are measuring the wavelength of the light from a certain single color source. You direct the light through 2 slits, so I know this is a double slit experiment, with a separation of 15.15 millimeters, and an interference pattern is created on the screen 3 meters away. You find the distance between the first and the 8th consecutive dark line to be 8 centimeters. What is your wavelength? Okay, so wavelength is lambda. is what I'm looking for. This is way too thick. Okay, and then they said, I have 2 slit. I'm dealing with double slit. The separation is 0.15, so that is D. Okay, the distance between the 2 slit, that is D, 0.15 millimeters. So that means that times 10 to the negative 3. You can divide it by 1,000. And the interference is created on a screen 3 meters away. Okay, the screen means the L. You find the distance between the first and the eighth. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, are 8 centimeters apart. This is 8 centimeters apart. So that means they indirectly gave you delta x. Okay, so let's count how many delta x there are. There is 1, 2, 3, 4, 5, 6, 7. Each of them is a delta x. So I have 7 delta x, and the total distance between the 7 delta x is 8 centimeters. So change that into meters. 0.08 meters. All right, so you want to just rearrange the equation. I'm going to punch it in later. I'm just going to do this. Okay, that is how long 1 delta x is. Okay, so that is my delta x. So 0.08 divided by 7. Okay, they ask you for wavelength. So take a look at what equation. I have delta x, I have L, I have lambda, I have D. So I'm going to be using this equation. Delta x over L equals to lambda over D. Okay, delta x, sorry I didn't divide it, so I'm just going to leave it in the bracket, divided by L is equals to lambda over D. Alright, so cross multiply. So I'm going to work out what 0.8 divided by 7. I'm going to multiply that 0.15 of the negative 3 divided by 3. Lambda is 5.71. Whoop, how many sig dig? 2 sig digs. 5.71 times 10 to the negative 7 meters. As I said before, these questions are not hard as long as you remember how to, like what wording goes with what symbols. Okay, so next one. Okay, one more thing. Look at your answers to see if it makes sense, right? If you have like your wavelength of light equals 5 centimeters, you know something went wrong, right? So make sure you double check your answers that it makes sense. All right, number 2. The third order dark fringe of a 652 nanometer light is observed at an angle of 15 degrees when the light falls in 2 narrow slits. How far apart are the slits? All right, so let's write this out. I have a third order, so n equals to 3. So meaning like the third line. And they tell you that the light, which is wavelength, is 652 nano. Nano is times 10 to the 9. Is observed at an angle of 15. So theta 3 is 15 degrees. When it falls onto 2 narrow slits, so I'm dealing with double slit. The reason why I keep stressing it is because the next lesson is a single slit and the equation is slightly different. You need to make sure you pick the right one. Okay, how far is the slit? So D. Pause the video if you need. Look for the equation you need. I have an angle theta, I have lambda, and I have D. So go up there and look for the right equation. Right, so are we okay that we're using this equation? As I said, we're always using the minima, okay? Between the dark and the dark. Okay, because it says in the nodal line. Right, like in here, they tell you that this is the dark fringe. So we're going to be using the dark fringe, which is the nodal line. Okay, so sine theta n is equals to n minus half lambda over d. Okay, so n is 3. So sine of 15 degrees is equals to 3 minus half lambda over d. So just be careful with your math. Okay, so 3 minus half times 652, the exponent of negative 9, divided by sine 15. So D equals to 6.29, okay, 30 times 10 to the negative 6 meters. So I'm going to keep 3 significant digits.